Welcome to the website demonstration video for the paper exploring the potential of graph neural networks-based methods. On the left bar, there are two components, try it yourself and example problems. We are currently on example problem 800. Here, you can see an image which represents the polyhedron for this problem. This problem has 500 variables and 700 constraints. The real polyhedron is of a very high dimension, and after performing PCA, this was reduced to 3 dimensions, which is as you can see in this image. Below, you can see pivot to optimal with default basis and SIB basis. The default basis is the basis where slack variables are all active and required approximately 75,000 simplex pivot to reach optimality. The SIB basis alternatively required approximately 150,000 simplex pivot. In this instance, the default basis was actually better than the SIB basis. However, if we look at example problem 801, the default basis required approximately 35,000 simplex pivot, while the SIB basis required approximately 16,000 simplex pivots. In our analysis, most problems actually works better with the SIB basis. Now looking at the two toggles, zoom in, dash out, and vertices visibilities. Starting with vertices, as mentioned before, there are 700 constraints, and if they were to each intersect with each other, then there are many vertices that forms this polyhedron. After performing PCA, we sampled a few vertices for you to visualize as seen by the gray dots. Next, there is also a zoom in and out button. This allows users to zoom into the problem and have a closer look at the different bases and optimality bases. The black dot is the default basis, which is at the origin. The green dot is the SIB basis, and the red dot is the optimal basis. Sometimes you may see the black dot is closer to the red dot than the green dot, despite the SIB performing better. This is likely due to noise in the PCA that was unable to capture the full details of the high-dimensional polyhedron. Looking at try it yourself, we can take a look at README first. This file contains all the information and instructions to operate this website. As you can see, this also explains what the black, green, red, and gray dots implies as well. More importantly, it teaches you how to use the upload LP problem here. Specifically, for example, on the SIB, it mentions to use a NumPy zip file with C as the key for the objective coefficient, A as the constraint matrix coefficient, and B as the constraint right-hand side coefficient. Capitalizations matters here. Moving on to the upload LP problem. The first thing is to choose the model. In this case, I will choose the SIB model. Then choose the problem and upload it from your own device. Once it runs, it will display results. On the left side, you can see the problem you had submitted. This may be a bit hard to read on larger problems, so we recommend you use Python to visualize your own LP problem if necessary. On the right, you can see a zoomed-in graph that displays your problem again with the black, green, red, and sampled gray dots. You can see the SIB basis and the optimality basis. Down the bottom, we can see the inference time, which is the time for the model to generate a starting basis. We can also see the accuracy of this basis as 60%. Finally, it also displays the SIB basis prediction and the true optimal basis. Next, let's try the LTP model with a bigger problem this time, so it will take some time to load. Once loaded, again we can see the problem on the left hand side, the zoomed in graph on the right hand side, the inference time and accuracy of 68%, as well as the LTP basis and the optimal basis below. Finally, we look at the IPMGNN model. Again, the problem is on the left and the graph is on the right. The information below this time is slightly different with the inference time, but also the objective gap, which is how far our basis objective value is away from the optimal objective value. We also see the constraint gap, which is how much constraint violation this prediction have.